Good morning, everybody. My name is Chris Jones. I'm with the University of Arizona, Gila County Cooperative Extension. Our first speaker today is Dr. Rivka Fidel. She's an assistant professor of practice at the Department of Environmental Science at the University of Arizona. She has a PhD in soil science from Iowa State University, and her BS is in environmental science from Union College in New York. She focuses her research on biochar chemical properties and their effects on soil, carbon and nitrogen cycling, nutrient and contaminant retention in soil, and soil greenhouse gas emissions. She also teaches soil and critical zone science classes and researches teaching and techniques relevant to those courses. So I know that you've got a lot of material to share. So we will pass it over to you. And so welcome, Rivka. How are you this morning?
Good, thank you.
Very good. How was your drive up today?
Actually pretty nice. Saw the sunrise over the Catalinas coming up from Tucson, and yeah, thank
Beautiful. You. Okay, then I guess we're ready. I'm gonna hand it over to you. Thank you.
Awesome. Thank you for the intro. And I've got, while we wait for more people to arrive, oh, is it still not? This was working a minute ago and now it just decided not to.
See that.
I think we can just try restarting the slideshow. It might be thinking that I'm in a different slide show right now.
If this is on start too long, it will just kind of stop. It's right.
Okay. Let's see if it decides to, oh, there we go. Okay. So yeah, while we wait for more people to arrive, I can kind of orient you to what I call my journey to the West. I'm from New York, as was alluded to, I believe. Got my bachelor's at Union College in New York. Has anyone heard of Schenectady, Albany? Anyone been to Albany or heard? Yeah, so it's near, that's northeast of Albany. Lovely leaf colors in the fall. And I was inspired to work on biochar because I was getting my degree in environmental science. And I was really interested in finding something viable to help us stop climate change. And when I learned about soil and soil carbon sequestration, I was really intrigued. Soil is kind of a big black box, so to speak, in climate models. It's one of the biggest unknowns, the hardest part of the global Earth system to model. And so that got me intrigued about soil. And then I heard about biochar and its ability to sequester carbon in soil. I was really excited about this. So I applied for various PhD programs, got in Iowa State, worked there for 7 years if you include my postdoc. And then I'm very happy to be now working at University of Arizona. And obviously these are really different environments. And I'm still fairly new to Arizona. So I've got some information, some data for you from Arizona, but I'm still very much learning about how to use biochar in Arizona and how to sequester soil and carbon in soil here. So let's see, we have a decent attendance on Zoom. We're good to go? Okay, so, the inspiration for using biochar in soil actually comes from a very different environment from here in Arizona. Show of hands, who's heard of terra preta? Everybody, all the scientists. Okay, terra preta are soils also known as Amazonian dark earths. These soils were quote unquote discovered to have relatively in recent decades to have much more carbon than in the surrounding soils. And it's thought that they were created by native Amazonian peoples thousands of years ago who either intentionally or unintentionally were adding char to soil. And when scientists found these soils, they were like, what is going on here? Because tropical rainforest soils are not actually naturally fertile. The rainforest plant species grow despite the poor soil because of their evolutionary advantages and because of the very high temperatures and moisture precipitation helps them overcome the low fertility of the soil. So unfortunately, a lot of people who are trying to farm in the Amazon and other rainforest areas resort to slash and burn tactics that are very detrimental to the rainforest. However, Terra Preta represented a type of hope where perhaps we could modify the soil in a way similar to ancient native peoples and perhaps improve the soil fertility. And Terra Preta is not the only example of soil that has this char in it. So in the Midwest and in basically most grasslands, there's frequent fires maintaining those grasslands, keeping back the trees. And during these fires, there's a natural byproduct of char that's added to the soil. And whether added intentionally or unintentionally, char lasts in the soil for hundreds to thousands of years. And as a result of these repeated fires in prairie and other grassland soils, a lot of this black carbon that we call what we call char when it's been in the soil for a very long time, a lot of this black carbon has accumulated to a degree where in many cases there's, like in Iowa, there's 10 to 30% of the total carbon is black carbon. So this could really be contributing quite a lot to the natural fertility of grassland soils, in addition to massively increasing the fertility of tropical soils. And we were able to verify that through, through NMR spectroscopy back at Iowa State University. So these examples of really fertile soils beget the question, can we make our own terra preta? Can we improve the fertility of soil and sequester carbon in soil by adding char to soil on purpose? So what is this biochar stuff? Well, what we should really be asking is, what are biochars? Because biochar is not a monolith. Biochars are an extremely diverse suite of materials made by pyrolyzing, i.e. charring, various organic materials at different temperatures. And both the source material and the temperature influence the properties of the biochar. You could use pretty much any organic material. So plants are the simplest way to go, but you can also use various waste material, corn cobs, bone, bamboo, wood waste, cardoon seed heads, rabbit droppings, for example. These are a very diverse suite. We wouldn't necessarily pick any of these, but it demonstrates that we can use a lot of things to make biochar. And in terms of sustainability and cost effectiveness, it makes the most sense to choose waste products that would not otherwise be sold or used to improve the soil quality in some other way. So we wouldn't want to go around pyrolyzing corn or something like that, the actual grains. We'd want to use the corn stover, the waste straw that is not harvested normally. So what is this pyrolysis process that we use to make biochar? Well, pyrolysis is the heating of organic material at high temperatures, but very limited oxygen. So you're cooking the biochar, essentially, baking it up without oxygen. And so you would take any kind of biomass solid fuel, add that heat, restrict the oxygen, and you get three products: gases, oils, and the char. And this process, pyrolysis, is the first step in fire. It actually happens all the time. That's why you end up with char whenever you burn solid fuel as a byproduct. It's not the only product. And what's happening during ordinary combustion is first the solid fuel pyrolyzes. So that heat transforms it into the char and oil and gases. When there is oxygen, the flammable gases encounter the oxygen at very high temperatures, and they undergo what's called oxidation. That's what creates the light you see in fire. So closest to the solid fuel is a low oxygen zone where it's the oxygen doesn't permeate so well into solid particles or big chunks of wood. And so that's why you still always get a little bit of char unless you very fastidiously chop up that char and stir the embers, stir the ashes until all the black is gone. So let's talk a little bit more about these different products and what they are, what you get from pyrolysis, and how they're different from the original material. So when you start with a biomass material, biomass just means any plant material, you would have these three main components: cellulose, hemicellulose, and lignin. I know those are big, big molecules there, but my point isn't for you to memorize these molecules. It's for you to see the difference here before and after pyrolysis. So we heat up the biomass at very high temperatures, high being about 300 to 800 degrees Celsius, so much higher than an oven would go, an ordinary oven. And then we get the char, which has, notice how it has that kind of honeycomb structure. We call that condensed aromatic carbon. And those are very, very strong bonds it has there, as opposed to these long chains of cellulose and hemicellulose. These have oxygens in between the carbons that help microbes degrade it. We'll get to that later, but they look quite different, right? And then the other products, bio oil have, and gas, those have much smaller molecules in them. And so the bio oil has molecules that aren't quite the same as gasoline, but it's close enough you could refine that into a drop-in fuel for cars, or you could burn it as a fuel oil for heating homes. And then finally, the gas product is called syngas. It's a combination of hydrogen gas, methane, carbon monoxide, and CO2. And of course, there's always going to be some water vapor, which I have not listed here. But those gases together can be burned just like natural gas, or they can be used to fuel the overall pyrolysis process, because you have to get that heat from somewhere, right? So there's 4 types and more if you start counting intermediate processes of biochar production: slow pyrolysis, fast pyrolysis, and then a new process called autothermal pyrolysis, and finally gasification. The difference between the fast and slow pyrolysis is what it sounds like. Slow pyrolysis takes hours to days. That's how long you have to keep the material hot for the process to be complete. Fast pyrolysis lasts for less than 1 second. Slow pyrolysis is really good for making char. Oh, all right, I don't have the pen enabled. Whereas fast pyrolysis is good for making oil, bio oil. And then autothermal pyrolysis lets you add a little bit of oxygen, just enough for a tiny bit of combustion to happen to keep the process going very, very efficiently. And this also has a good oil yield. This is a very new process designed by researchers at Iowa State University. Some of my former collaborators are working on it, and they just have, I believe, a pilot scale autothermal pyrolyzer going. So I don't have any diagrams for you, but it does exist and it's very efficient. And then last but not least is gasification. Like it sounds like, it's optimized to yield that syngas. So who wants to hear about these in detail? Yeah, a few, okay, I'll go for it. We gotta watch the time though. So slow pyrolysis, like I said, you heat it up slowly. And Darren, your next speaker, will go into this in more detail. But slow pyrolysis is what's used to make traditional charcoal, whereas biochar is intended for soil application. It's really essentially the same process. Some very old-fashioned methods include, which the Amazonian peoples might have used, include just digging a pit of in the ground, dumping some biomass in there, throwing a match in, letting it ignite just a little bit. You have a little bit of complete combustion happening to provide some heat. And then when it's hot enough, you bury it. And so it smolders, and that smoldering is in fact pyrolysis. Burying limits the oxygen that can come in. And so you end up with a nice biochar at the end. You cannot, through most of the slow pyrolysis methods, especially the small scale methods, you can't really collect bio oil. So another one of my former colleagues at Iowa State founded a company, Char, A-R-T-I, and then Char. He makes a small scale kind of, I would call it slow pyrolysis, pyrolyzer that does let you collect the bio oil, but it's very unusual to find something like that. So yeah, usually these are just, these can be small or large scale, but most of the backyard pyrolyzers on the market are some kind of slow pyrolysis process. So pros to slow pyrolysis, you get a lot of char, but cons, it's slow. And if you're not careful, you can produce a lot of smoke, which obviously causes air pollution, but also negates a lot of the climate benefits of biochar because it causes localized warming. Then fast pyrolysis is fast because it uses a very unique process where there's a cyclone of sand, hot sand. So you introduce finely ground feedstock, very small particles, and then the sand, it's mixed with fine sand that's spinning around at high velocity in a cyclone of not air, but usually nitrogen gas. And that very, very hot sand touches the biochar particles and just, well, touches the feedstock particles and just instantly pyrolyzes them. So this is why it happens in less than 1 second. The sand stays super hot and heats up that biochar really, really fast. And then the gases are collected, and some of those gases will condense down. They're cooled and condensed down and collected through this quenching system here. And then you keep that bio oil. So usually you have to send the syngas around to a burner and burn that syngas to keep the whole thing hot. So you don't usually get much syngas out of this process, mostly bio oil and char. And then gasification. Like I said before, you add some more, I'm skipping autothermal because that one's really new. But like I said before, you add some extra oxygen, you get more gas out of this process. And usually it's kind of a stratified process where the air is introduced through these inlets on the side. So the oxygen isn't distributed evenly. And that's on purpose so that you can have some pyrolysis still happening, and just a little bit of oxidation to convert a little bit more of that feedstock into the into syngas. And at very high gasification temperatures, you might not get significant char out. You might get mostly ash. At lower temperatures, you can get good biochar yield. It might be very high in ash, which we'll talk about. It is good for some things, but not others. And there's some other interesting stuff going on here that's beyond the scope of this talk. Anyway, and so these pyrolyzers of different kinds can be also made at very different scales, ranging from a small backyard scale where you would maybe put a few pounds of feedstock in and yield about 25 to 50% of that. And you can then scale it up to many pounds per day, maybe for a greenhouse or nursery operation. And industrial operation would be anywhere from 1 to 50 tons per day yield. And then at these larger scale, so there's a lot of debate over which scale is most sustainable. And the answer isn't exactly clear yet, but I'm going to tell you a little bit about some pros and cons. This illustration is of how large scale might work. So you would collect the biomass at one location, bale it, store it, and ship it to another location where it would be pyrolyzed. And then in the case of fast pyrolysis, you would get some bio oil, which would have to be transported elsewhere to be refined. And then the biochar yield could go back to the farm and be applied to the soil. However, what do you notice about this diagram is happening over and over again? Something's happening here. Anyone want to shout it out? I know yeah, a lot of trucks. So the cons to a large scale is that you have to transport the material a far distance. For bioenergy purposes, it's been shown that about 30 miles is the limit that you would want to go. It's less certain about biochar in particular. What distance is okay. But yeah, there's a transportation cost, whereas, like I said, those small scale pyrolyzers usually don't yield much oil, and you certainly wouldn't want to refine that oil on your own farm or garden location. So large scale lets you take advantage of economies of scale, but you have to watch out for the climate impacts. So any questions about that stuff before I move on? Yeah. So now we've learned how to make biochar. Let's learn about why we would even want to use it. So, there's a lot of potential benefits. I know it's hard to see that. I have another list that's easier to read. But there's a lot of potential benefits. For the soil, we could increase water retention, reduce bulk density, and overall improve soil fertility, hold on to more nutrients, reduce the amount of nutrients that end up in the groundwater, nearby rivers and streams, and sequester carbon. And then in terms of the atmospheric benefits, we have reduced carbon in the atmosphere, so sequestering carbon again. You could also reduce soil emissions, especially methane and nitrous oxide are a big concern, especially where manure has been added to the soil. So biochar can reduce that. And then when you're storing manure somewhere or adding it to the soil, you can reduce odor from that, or just from kind of any industrial agricultural operation. Biochar can be used to filter odors out of air waste streams. Okay, so I'm going to go through how exactly biochar does all these cool things. So how does that work? Well, first off, the main motive behind the initial motive, I should say, behind applying biochar to soil is carbon sequestration. How does that work? Well, it happens because plants first take up the carbon dioxide out of the atmosphere, and then that carbon gets locked away in the biochar in a very stable form. And the reason why it is stable is due to its chemistry. So those honeycomb structures that we looked at before are very resistant to microbial degradation. You can think about it as like reinforced pillars or something in a building, right? So you see these little double bonds here, those are reinforced. So what happens is in the soil, normally, without pyrolyzing the biomass first, you would end up with microbes just gobbling all that stuff up. They love that fresh biomass, and they will reduce the amount of carbon to anywhere from 5 to, well, it depends how long, but you'd only get 20% of that original, maybe usually less, more like 1 to 2% once you extend this out over decades. This is only going out to 5 years, but over decades, you would expect only 1 to 2% of that original carbon to remain in the soil because of those hungry microbes. Now, when those microbes see biochar, they're like, nah, that doesn't look too tasty. That's too hard to degrade. There are some specialists that can do it, like rot fungi that degrade wood, but most microbes are not going to eat this. And so it persists in soil instead for hundreds to thousands of years. So you lose some carbon first to those biofuels, which are then burned, but most of it, well, not most of it, most of the biochar that you apply to the soil will remain there for hundreds to thousands of years. So between 25 to 50% of that original carbon stays in the biochar, and that will stay in the soil. So if you look at the overall cycle and how that's affected by adding biochar, if a plant dies and just decomposes, or if you were to burn that plant material, virtually all the carbon eventually would end up in the atmosphere, so 99% or so. However, with pyrolysis, we sequester that 25 to 50% in the biochar, burn the rest of it, and for fuel. And so only about 50%, 50 to 75% ends up back in the atmosphere, whereas 25 to 50% stays in the soil.
Can I ask a question on that?
Mm-hmm.
So if we're using our slow pyrolysis biochar kiln, would it be 50% carbon that we're able to sequester because we're not being able to capture the energy? Or would it,
so
what amount would that be?
No matter what you do with the energy, the carbon that's not in the biochar is going to the atmosphere or getting decomposed somehow. So during slow pyrolysis, some of those gases are released to the atmosphere, and with a flame cap pyrolyzer, I would expect that to be mostly carbon dioxide. And so that's where that's going. A little bit of the carbon ends up in during slow pyrolysis, ends up as oil that's condenses on the char. So the char can have a little bit of an oily film in places, and that's mixed with some sugars, and microbes have a much easier time decomposing that bio oil compared with the biochar. So that small amount also contributes to this 50 to 75% that ends up in the atmosphere. I'm glad you asked though, because slow pyrolysis biochar stays in the soil longer than fast pyrolysis biochar.
But we would be catching 25, 30%
You
more
would,
likely?
Yeah, so there's pros and cons. The slow pyrolysis biochar will last longer in the soil, but you don't get those, you don't get the energy out of it. Yeah.
Okay.
But you can cook your dinner on top of it if you really want. Okay. So biochar, we said, does a lot of other things like hold on to water and nutrients. How does it do all that? Well, biochar holds on to water, and some of that water can contain nutrients because biochars are porous. They're kind of like sponges. They have little holes, little pores in them. And those are usually from the plant cells that have been locked in shape during pyrolysis. Whereas if you let the biomass just decompose, it'll turn into mush. It's still porous, but porosity we would expect to be a bit lower if it were to decompose. And then that porosity varies, of course, according to the type of biochar. Then biochar retains nutrients and can remove contaminants or at least reduce their bioavailability, because biochars are what we call sorbents. Nutrients as well as contaminants, quote unquote, stick to biochar in a process called sorption. So how that works is biochars have on their exterior, this is a very average biochar we call molecule, but biochars have thousands of molecules in them, perhaps millions of different molecules. But if we just take our pretend biochar molecule here, we can see that it has these oxygen-containing functional groups in red, and those oxygens carry a negative charge, and a lot of nutrients and contaminants, these are all nutrients in the picture, a lot of nutrients like ammonium, calcium, magnesium, potassium, those have a positive charge, and opposite charges attract. So the charged nutrients adsorb to the biochar instead of leaching out into the groundwater. They stay in the soil longer where the plants can get them. And sometimes chars will attract some negatively charged species as well. So these sorbed nutrients are available to plants, and the biochar holds onto them for the plants to use. Who's heard about soil pH before? Soil pH. Okay, so soil pH is a very important property. So we want it to be in a certain range for plants. Has to do with the hydrogen ion concentration in soil. So if it's too high, that's not good. If it's too low, that's not good either. A lot of soils, especially in regions with high precipitation, high rainfall, have soils that are too acidic for average crops like wheat, corn, or soy. And so those soils need some kind of amendment to increase their pH. And we call those liming agents. And biochar is itself a liming agent. And so a lot of the success stories of using biochar on tropical soil are due to its ability to raise the pH, which is what's going on in this picture. When the pH is too low, other nasty things can happen, like toxic metals being too soluble in the water, in the soil, and then getting taken up by plants too much. So metals and aluminum become a problem at these low pHs, and biochar can alleviate that. So that's what's going on in this picture. We have increasing amounts of biochar added to this acidic soil, has pH of only 4.6 and far too much aluminum in it that's available to plants. And then as we increase the amount of biochar, the plant growth increases, in part because that aluminum concentration is decreasing as a result of the increasing pH. And biochars not only help plants, they also help microbes, soil microbes, that can in turn help plants. And they do this in several ways. Small amounts of that bio-oil material that I was talking about can feed microbes. That's a very short-term effect. There's also some sugars, again, short-term effect. But long-term, biochars, because in part of their porosity, those tiny little holes in the biochar, can create homes for small microbes and keep them safe from larger microbes. Microbes can also just kind of stick to the biochar and hang out there and make it a good place for plants to get nutrients from those microbes that help decompose organic matter. And biochars, fun fact, are semiconductors, and microbes need electrons and they produce electrons. So there's some weird stuff happening there that we don't quite understand with electrons moving around through the biochar. So we've talked about a whole bunch of potential benefits here, and I just have them all listed for your reference. But you might be wondering, is biochar too good to be true? Can we have our cake and eat it too? Can we have all these things at once? Well, the answer is it depends on a lot of things, mainly the biochar and soil type. and finding a good match between the two of those. Why haven't we figured this out yet? That sounds simple, right? Sounds simple? Well, soil is anything but simple, unfortunately. Soil is arguably the most complex material on Earth, and it's been named the final frontier in science by Science magazine. And the reason for that is because soil has many interacting parts: minerals, microbes, organic matter, water, air, all interacting at once, thousands of chemical reactions possible at once, as well as physical interactions. Adding biochar to that adds an extra layer of complexity. So it's very hard to predict what's going to happen when you add any given biochar to soil. So given this complexity, when should we actually use biochar? And how do we tell which biochar to use? Well, there's many trade-offs. We don't always see all the benefits at once of biochar. There's no one biochar that's optimal for everything, every soil. That's very, very, I don't want to say impossible, but it would be extremely difficult to create such a thing. And therefore, we must match the biochars with the appropriate soils using a decision tree approach. If your soil has certain properties, then you need a biochar with certain properties to match. So important biochar properties to consider include surface area, porosity, its absorption capacity, so that sticking phenomenon we were talking about, as well as ash content and carbon stability. And then the soil properties we want to consider are particle sizes, so like texture, porosity, organic matter, minerals, and nutrient content. And these all interact with each other as well. So this process can be quite complicated, but despite the uncertainty, we can still gather some clues, look at the evidence, examine it critically, and come up with some general inferences and very broad recommendations. So the key to doing this is recognizing that every soil has a particular limitation, something that's preventing plants from growing optimally. So we would call this the limiting factor to plant growth. If we can identify that factor and alleviate that, choose the right biochar to alleviate that, then we can improve plant growth. If we choose a biochar that doesn't fix the soil's problem, well, of course, you're not going to see much improvement. So let's go through some problems one by one here. 15 minutes or less? Oh, okay. Yes.
There will be a few questions at the end, so maybe save about 15 minutes.
Great. That's what I was hoping for. Okay, so first problem, structurally degraded soil. This means that soil doesn't have good aggregation, good clumping. It could be too dense, could be compacted from too much machinery running over it. This is the easiest problem to solve. Biochar naturally has a low density and high porosity compared with damaged soil, so adding some will of course alleviate that. You might want to choose an especially high porosity biochar for this task, but pretty much anything will work. And this is an example from Iowa State University. There was some soil that was used in construction. So it was dug up, moved around, mixed up all over the place. The topsoil was mixed up with the subsoil and everything was out of whack. We added some char, which was actually intended to be charcoal. Watch out though, if you buy charcoal that's intended for home use, it often has some chemical additives you don't want to add to soil. But this was, this char had not received those chemicals. So this char was ground up and applied to the soil. And in the middle of this picture on the upper right, you can see that the corn that was planted on that soil grew much better than in the surrounding soil that did not receive any char. So structural problems, easy to fix. Another relatively easy fix is acidic soil. So the pH is too low, like tropical soils. And in the United States, we have a lot of soils with these problems along the East Coast. A lot of acidic soils there, and maybe mildly acidic soils in Iowa, in the Midwest, Iowa, areas with high precipitation. So most biochars are alkaline. They have a pH greater than 7. And so that's like those alkaline waters you see in the store. They also have pH greater than 7. So for these acidic soils, you would just, almost any biochar would work, but you would want to optimize, you would choose in a particularly alkaline biochar with a high, what we call calcium carbonate equivalent. Calcium carbonate is what we usually add to soil to increase the pH, also called agricultural lime or calcite. And so this is the percent effectiveness compared to calcite. So biochar might not be able to replace calcite, but what it does is it lasts a lot longer in the soil and keeps the pH stable for much longer in the soil. So what we're seeing here in the middle is the effect of temperature. So the CS stands for corn stover, and then the numbers stand for the different temperatures. So as we go from 300 degrees Celsius to 500 and then 600 degrees Celsius, we increase the alkalinity of the biochar. And so temperature has a definite effect. And then in terms of feedstock, it's really hard to see here. I mean, we have some wood chars on the right, but the effects are kind of inconsistent. If you just use broad classifications like wood or grass or agricultural waste, what matters is the alkali metal concentration. So calcium, magnesium, potassium, sodium. Those, during pyrolysis, those bind to, those are cations, they have positive charge. They bind to anions, negative charge, that raise the pH. So it's kind of complicated, but the chemical composition of the feedstock and the temperature of the feedstock affect the alkalinity of the biochar and its ability to alleviate soil acidity. So we can see when biochar was added to an acidic soil, it performs really well relative to these controls where agricultural lime was applied. And where exactly do these come from? These alkalis that raise the pH. So the material that we find in agricultural lime, calcium carbonate, can be found in biochar as well, as in addition to similar compounds that contain that CO3 minus, what we call carbonate. And then there's other inorganic alkalis that have oxides, see the oxygen, hydroxides, OH. And then the surface functional groups that we talked about can also have some alkalinity to them. Any questions about this? We're doing okay with the chemistry. I've tried to keep it light. You're good? Okay.
Oh, this is light.
And then this is one of the more complicated ones, but the way I know the graphics are complicated. I'm trying to keep the words light. Yes.
I was just curious, because you had a really good graph that shows the calcium carbonate equivalent, but you have something that shows the cation exchange equivalent? Like, is there something that shows like 2-to-1 play? Like how well? Yes.
Okay. I have that coming up and I will point it out to you. It's not quite cation exchange, but it's the surface functional group concentrations. Sam over here, who's worked in the Blankenship lab, one of my collaborators, has measured cation exchange, and we can help you find those data. Yep. So there's plenty of things that raise pH in biochar, both organic and inorganic. So that's one of the simpler things to work with. However, in dry environments, like here in Arizona, usually we're at the opposite end. The pH is either high enough or possibly too high. And another problem we have here is salts. So for these high pH soils, we would want to act oppositely, use a lower temperature pyrolyzed biochar. Now, for salt, affected soils. Soils with too much salts, whether that's sodium chloride, table salt, or like calcium sulfate, which is gypsum. We want to apply a biochar that doesn't have too much salt. So we don't want to make the problem worse. So we want to choose a low salt biochar. This shows, oh gosh, I know it's hard to read. So this shows a variety of different feedstocks that were used to make the biochar. And these were all grown in Arizona, and I've sorted them according to how much water they retain here. And the details are not quite as important. These were all made at 500 degrees C. What I want to show you is that the grassy and leafy feedstocks, the Sudan grass, wheat straw, wheat is a type of grass, as well as hemp, and I think the leaves were paralyzed there too, or? Mhm. Okay, thank you. So the hemp, when it was paralyzed, was basically the whole plant except the seeds. So that has stems and leaves in it. But basically, if you have enough grass or enough leaves, you're going to retain more water. Then wood biochars are in the middle. And then at the end, we have some other biochars here. So palm tree trimmings can have a variable amount. And I think that's because both the bark and the leaves are harvested. So you can get kind of anything going on there. Alfalfa was kind of low. That is a leafy feedstock, but for whatever reason, the porosity was probably a bit low. And then cotton waste was kind of low. And an interesting thing that was observed during this research in the Blankenship lab at U of A, my collaborator, was that after soaking the biochar in water, the biochar was able to retain even more water. So biochar that has been wet for a while can retain more water. What's probably happening is that it's becoming what we call more hydrophilic, water loving. It attracts more water to it when it's been soaking in the water a bit longer. There's some chemical reactions that make it more attractive to water after it reacts with the water. So what do we conclude from this? Well, if you want to retain lots of water, choose a grassy or leafy feedstock to make your biochar. And you may want to pre-wet your biochar, soak it in some water before applying it to the soil. If you apply this biochar to the soil completely bone dry, it may actually suck some moisture from the soil and deprive your plants from moisture. So definitely at least irrigate your soil immediately after applying the biochar.
Could I ask a question
Yes.
on that slide?
Yes.
So how about available water? So how well does the biochar hold that water or release it to the plants to be able to use?
So that was not measured in this study. However, it is shown that biochar can improve plant available water. So this is water holding capacity, which is how much water that the biochar will hold onto after allowing it to freely drain, in this case, in a column or funnel. But the plants also care about the water that is, well, they can't get the water that's stuck in pores that are too small. So if the biochar pores were too small, then the plants couldn't get that water necessarily. And so thankfully, it is shown that especially in coarse textured sandy soils, biochar does increase plant available water. You would likely see a lesser effect in soils that already hold plenty of water. So you would not want to apply biochar to improve water holding capacity of a soil that already has a good amount of water holding capacity or a good amount of plant available water.
But even in a clay soil, so it's in a good line and in a good loam, maybe it's not having that much impact. But in a clay soil, it should add organic matter and create more macro spaces for for the roots to be able to grab that water?
Yeah, so sometimes biochar can improve plant available water in a clayey soil. Part of what it does there is the clay particles are, the spaces between them are usually too small for the plants to get as much water out. So biochar can push the pore size distribution back towards the happy medium in the middle between 2 and 10 microns-ish. And it can also improve pore drainage, which is very common in clayey soils.
Right.
So you were correct. Was that, I didn't know if that question was caught because you have a mic, but it's,
Hopefully it's all catching.
okay.
And then back to our sandy soils, which I can really see it helping because it's going to hold water in the root zone for a longer amount of time. So that's going to be good. We got our loamy sands and our sandy loams. That's very common here.
Yep.
Okay. Great.
Yep. Yeah. So here in Arizona, we have a wide variety of soil textures, but in the sandy, from sandy to sandy loam soils, for sure, biochar can definitely make an improvement. And I've got some examples, if we keep going here, that might help answer that a little bit more. So our other problem that I mentioned was a salt-affected soil, salty soils. And I said we want to use a low salt soil. We measure salts using electrical conductivity because salt water conducts electricity better than pure water. And so what we see here is that citrus wood, salt cedar, and medjool palm have the lowest electrical conductivity among the tested biochars. These were all grown in Yuma, Arizona. These are the same biochars as on the previous slide, but I've just sorted them by EC this time. And these 3 chars have ECs that are not predicted by back of the envelope calculation to cause salinity stress in plants. So I just adjusted this for dilution factors and converted the units. So 4 decisiemens per meter is the limit for salinity stress. So these 3 chars should not cause a problem. And notice that especially the citrus wood and salt cedar are wood biochars made from the not the bark, not the tree, not the leaves, the wood of the part of the plant. The other biochars had much higher salinity. So this is a major concern for already saline soils. We don't want to make them more saline, but all is not lost. The salts that increase the electrical conductivity, the salts that cause problems, are soluble. So we can wash them away with water before applying them, before applying the biochar to the soil. So you could just put biochar in some kind of sieve, run a bunch of water over at home. This is a very rudimentary method. I haven't tested it, but in theory it should work. And then you also want to watch out for biochars that have been grown from feedstocks that were grown in very salty soils, because the plants take up the salt. And then when you pyrolyze the biomass, the salts get concentrated in the biochar. They do not go to the bio-oil or to the gas fraction. So this is especially a problem for high temperature biochars. These are all made at 500 C, like on the previous slide. So that's a moderate temperature here. And we would anticipate higher temperatures would be not so good. So another argument for keeping the pyrolysis temperature medium to low when applying biochar to desert soil. Biochars can also alleviate salinity stress by providing potassium, which helps plants become more resilient to that stress. It helps them control osmosis a little bit better, and so they can get more water that way. And what we were getting at before, the cation exchange, those surface functional groups, they hold on to the good cations, the calcium, magnesium, potassium that the plants use for nutrients better than the bad cation, sodium, which exacerbates salt problems for plants. So that's getting into salinity versus acidicity, which is a whole another topic I'd be happy to talk about later. But moving on, that same property, the sticking, the cation exchange process that we were talking about before, can help the biochar retain those nutrients. And the ability of the char to retain those nutrients depends on the charge of the nutrients and the temperature of the biochar, and the temperature of the biochar affects the charge of the biochar. So we need to oppositely match the charge of the nutrient of interest with the charge of the biochar. So if you want to sorb cation nutrients, ammonium, magnesium, calcium, potassium, you want a char with lots of negative charges, and we can achieve that by pyrolyzing at a low temperature. Now, oppositely, with negatively charged nutrients like nitrate, phosphate, sulfate, so things that provide phosphorus and sulfur exclusively are found with a negative charge. Nitrogen can be positively or negatively charged. So you have to look at what's in your fertilizer, figure out what's going on here. But if you see in your fertilizer, or you see that your plants are limited in terms of phosphorus or sulfur, then you definitely want something that will absorb these anionic nutrients, negatively charged nutrients. You want to choose a higher temperature biochar that will absorb those better. This sort of answers your CEC question a little bit, I hope. So CEC is proportional, very close to, not necessarily equal to, the functional group concentrations charge. That's what milliequivalents are. This is per gram. So again, the CS stands for corn stovers, and the numbers indicate the temperature, add 2 zeros. So the fast pyrolysis corn stover biochar had the most total functional groups. And then the functional groups, the charge that they have is sensitive to pH. We're getting into complicated stuff from an advanced course I teach, but it sounds like you're really curious. So I'll dive in just a little bit. So these functional groups, when we're looking at soils of typical pHs, we would care most about the functional groups in the 5 to 6.4 pKa range. That means that at those pHs between 5 and 6.4, that's where the biochar is going to flip from having a positive to negative charge. Then at the higher pK functional groups, they're not going to react as much in the soil, but what happens here is these guys, the 5 to 6.4s, contribute the most, in theory, to cation exchange, okay? Because those functional groups will become negatively charged at normal soil pHs, whereas the anionic nutrients are going to be more sensitive to the higher pKa functional groups. I'm happy to define pKa later, but just think about it as like a pH thing for now. And so those higher functional group, higher ones, which like this functional group over here, the hydroxide, would contribute more to the anion sorption. Okay, so I said that there's pH sensitivity. This unfortunately complicates things, so just hold on to your hats for a second. So what happens is we said that as we increase temperature, sorption of cations decreases and sorption of anions increases. Nitrogen comes in 2 flavors, ammonium and nitrate. Ammonium has a positive charge and nitrate has a negative charge. And so if we So temperature has an opposite effect for those two. And then pH has an opposite effect too. So if we increase pH, we're going to increase sorption of ammonium, positively charged nitrogen species, and decrease sorption of nitrate, the negatively charged species. And what's happening there is as we increase pH, charges shift on the surface, but from mostly negative to mostly positive, attracting the oppositely charged species. Again, advanced stuff. But basically, desert soils have a high pH. So they're going to be naturally better at maintaining ammonium. And we can augment this by pyrolyzing at a low, moderate to low temperature. So we can retain more ammonium in desert soils by pyrolyzing at the low temperature and potentially reduce what's called ammonia volatilization. So ammonia is a gas. If the soil doesn't hang on to the ammonia, it will go into the atmosphere. So biochar produced at a low temperature will hold on better to the ammonium, reducing the chance of it becoming ammonia and going into the atmosphere. So we can see here these opposing effects create a lot of complexity. They also create trade-offs. You can't have everything. And it's an example of how no single biochar can do all the things it wants. So no single biochar is going to be optimal for ammonium and nitrate sorption. No single biochar is going to be hold on to potassium and phosphate, for example, the same. Now, how are we for time? Oh, okay. So I have some examples, basically this showing that this works in real life. Yield increased when you added a combination of biochar and compost together with irrigated soils. And there's some crazy complicated stuff that happens with greenhouse gas emissions. So those are affected by both pH and moisture. And basically, I have a bunch of graphs here that summarize my dissertation. So what happened is, we don't actually know, but biochar was increasing moisture, which in theory should increase nitrous oxide emissions, but we saw a decrease. So possibly the biochar was hanging on to that nitrogen just enough to reduce the emissions, but in a different test in greenhouse instead of in the lab, we saw that there was more nitrous oxide emissions when the biochar held on to more nitrogen. So if there's more nitrogen in the soil, you could have more nitrous oxide emissions, but if the biochar holds onto the nitrogen really tightly, it could prevent the microbes from getting it, and then the microbes don't turn it into the greenhouse gases. So, and this is just showing that no one biochar is perfect. So you can see the data here all over the place, no matter what they are. And just on a side note, biochars do contain some nutrients, but it's not enough for them to be a all-in-one fertilizer. You would have to mix the biochar with compost or with a fertilizer or something, or add it with fertilizer at the same time. And then the biochar mainly helps with soil fertility by holding on to those nutrients better, like we talked about before. So manure biochars are unusual. They have a bit more nutrients in them. And then biochar can help with contaminated soil by holding on to those contaminants. It's really good at holding on to heavy metals. Most biochars will hold on to heavy metals quite well, reducing plant tissue concentrations by 17 to 39%-ish. It's harder to make a char that holds on to anions in general, but you can make one that will hold on to negatively charged contaminants like arsenic, which is found as arsenate. Make it at a high temperature, like with the nutrients, and then you could add stuff like iron before pyrolyzing to augment that. Other contaminants, who's heard of PFAS? Perfluorinated compounds? Forever chemicals. So there are organic chemicals that come from like non-stick pans, as well as dryer sheets and firefighting foams. And there's groundwater in Tucson that's contaminated with this. And they don't put it in the drinking water, but they're trying to clean it up. Biochar might help with that, especially if you make it at high temperatures. This is true for a lot of contaminants that are not very soluble in water, organic contaminants. And biochar can be used for tons and tons of things that I'm not going to get into. But how exactly do you choose biochar for your soil? Well, you identify the problem that needs to be fixed. You figure out which biochar is best suited based on what I talked about for your problem. And if you're buying a biochar instead of making it, especially if the seller doesn't say how they made the biochar, take those advertisements with many grains of salt. They might not work for your particular soil. So always test it out in a little patch of soil for yourself. How do you do that exactly? How much should you apply? For most uses, 1 to 2% amendment is good enough, maybe a bit higher for a potting mix, potting soil. So in your garden, you might apply 1/8 to 1/4 inch of that char and then mix it in to a 1 foot depth, or we'll get into this other ways to apply it. And that's equivalent to anywhere from 5 to 20 megagrams per hectare. So that's metric tons per hectare. And again, test a small area. And then if the soil is really good already, and you want to improve like water retention or other physical properties, you might have to add a lot more. And you need to watch out at these high concentrations of biochar, because a small toxicity issue with biochar can occur during germination. And usually we don't observe it until these high concentrations of biochar. So you might want to do a germination test first, or just ask the seller, have you done germination tests with this biochar? Do you know that it's safe at high concentrations before applying very large amounts to soil? How do you apply it? I'm getting there. How do you apply the biochar? Well, the first option is to till it in, so mix it into the soil. This prevents losses of biochar, especially in the desert. You don't want the biochar to blow away. However, if you till the soil could blow away. So you need to irrigate no matter what with all these options after applying the biochar. Tillage also disturbs the soil, breaks up aggregates, and so it's not good for the soil long-term. One-time thing in a soil that has low organic matter to begin with, like desert soils, probably okay. But this is usually what's used in research. Then another approach is to co-compost the biochar and then apply the compost as you would normally apply compost. This approach is really nice because it infuses the biochar with nutrients and enhances the quality of the biochar if you choose the right biochar and the right compost, of course. Then that's time consuming. So what if you want something faster? Well, you could inject the biochar. You can make a biochar slurry. The company I mentioned, Artichar, A-R-T-I, they make what they call micronized biochar, very fine biochar that will stay suspended in liquid. And you could spray that on through your irrigation system, actually, and it will flow into the soil with the water. However, this can be logistically challenging. If the particles are too large, it can clog up your equipment. You can coat seeds with biochar. And I don't know if anybody's selling biochar coated seeds right now, but that's also a process you would have to learn how to do. So logistically challenging. Last but not least is surface application, my least favorite method. It's easy. You don't disturb the soil. You just spread the biochar on top. The problem is in the desert, yeah, it'll blow away. So you have to cover it with something as fast as you possibly can and irrigate as fast as you possibly can to keep it from blowing away. And that dust pollution will negate a lot of the benefits of biochar because it causes localized warming, reduces air quality, and just literally removes some of the biochar that you're trying to apply to the soil. However, if you apply the biochar wet, you keep the soil moist with irrigation. Pre-wetting helps with the salinity too. If you keep the biochar wet, you're gonna have less dust. So what's the bottom line? Could biochar actually make a difference? Well, it could offset up to 12% of greenhouse gas emissions annually. And that's going to be greater when it increases crop yields more and when you're replacing intensive fossil fuels like coal. Whereas if you combust the biochar, that would only offset, not biomass. If you combust the biomass instead of pyrolyzing it, that will offset about 10% of emissions. So we've gone over a lot of pros and cons here. Bottom line is you have to match biochar with the soil. You have to apply it carefully, and you have to make the biochar carefully so we don't negate all the benefits of biochar. So the bottom line is biochar is not a single silver bullet. Biochars are indispensable tools for climate change mitigation and soil management. And with wise use, we can do great things with them. Thank you.
All right, well, thank you. Ben, did we get a few questions on the?
We did. Do you want to ask them now or wait for the?
You know, we've got a big window for Q&A. So why don't we take it, if the people who wrote the questions don't mind, we can field those after Darren's presentation and take our 15-minute break.
Real quick, I'd like to again thank the Blankenship Lab for data and for helping me out here. You can contact me at rfidel@arizona.edu, and I have a Twitter, Rivka Fidel, as well. So I can take many questions that way too.
So Dr. Fidel, thank you so much. I think you've got an extension educator's heart, so very good. We're going to take our break right now. It's 10:15. We'll come back at 10:30. We'll hear from Darren McAvoy talking about how to use this, we learned, it's called slow paralysis, a kiln that we'll be able to use this with. And come back. He's got about an hour for his presentation. And then we've got a whole half hour for Q&A. So we'll get into the questions you have for Dr. Fidel.